بسم الله الرحمن الرحيم. حياكم الله جميعا. First of all, I would like to welcome all of you tonight in this special event organized by the Department of Computer Science at the College of Computer Science and Information System at Najran University. Our guest tonight is Dr. Ali Alqahtani, who just graduated from Auckland University in the United States with Doctor of Philosophy in Electrical and Computer Engineering. Dr. Ali graduated from Western Michigan University in 2017, and he got his master's degree from there. In 2012, he graduated from King Khalid University with a bachelor degree in Computer Networks and Communication Engineering. During his PhD, he has been publishing multiple papers in multiple journals and conferences, and his research interest in wireless communications and IoT and embedded system. I don't want to take too much time of his presentation tonight, and thank you, Dr. Ali, for being here and to present your, mashallah, great achievement. You can start, and thank you so much.
Good evening, all. Thank you so much, Dr. Yusuf, for organizing the webinar. And thank you so much for the introducing myself to the attendees. So the title of the webinar is a novel non-coherent OQPSK detection based on interactive Kalman filtering with applications in ZigBee receiver. The agenda of the talk today is divided as follows. I will highlight on the abstract, and then I will talk a little bit about the motivation and challenges and list some previous related works. Then I will lay the groundwork of this research by giving you guys a brief introduction about ZigBee technology and Kalman filtering technique. I will introduce you with some basics on the digital communication systems. Then I will illustrate the methodology, which is based on interactive Kalman filtering. Then I will display and discuss the results and simulations. Then I will list the contribution that we make in this dissertation. Then I will conclude and list some future work. So the research framework, the theory is to apply a Kalman filter to non-coherently detect the phase changes of offset quadrature phase shift keying modulated signal. We apply the concept in ZigBee technology, and we use MATLAB for the implementation. Abstract. OQPSK is a digital modulation technique where the phase of the carrier signal is changed in accordance with the binary symbols. This research seeks to implement an optimal estimation algorithm that could be used to non-coherently detect the OQPSK modulated signal, and the objective is to minimize the phase deviation error. The technique is based on using two linear Kalman filtering, which are coupled together to be used as a priori phase to an extended Kalman filter, and to generate an estimate to the phase coefficients. We choose to implement the proposed method in ZigBee receiver because it's promising low data rate wireless personal area network technology. The results in this study show that interactive Kalman filtering technique estimates the changes of the carrier phase of the OQPSK modulated signal correctly. And we tested the robustness of the proposed method in the presence of Gaussian noise, non-Gaussian noise, and co-channel interference in order to check how the system behaves with different wireless propagation environments. Motivation and challenges. Software-defined implementation is possible nowadays due to the rapid evolution in programmable devices, such as FPGA microcontrollers, which serve as a motivation to replace most hardware devices in most modern digital receivers. ZigBee actually is subject to nonlinear noise and interference, such as non-Gaussian noise, co-channel interference. Therefore, by 2023, maybe at least 20 billion devices will be connected by ZigBee. The traditional carrier phase tracking is compromised in handling these kinds of severe propagation environments because it's based on traditional technique, which is based on analog communication. And now we are in the era of digital communication. So we need a robust and optimal technique that could address all these obstacles for ZigBee and for all the digital modulation technique. The objective of this research, we have three main objectives. One is to implement an optimal estimation algorithm that could be used to non-coherently detect the OQPSK modulated signal. The second objective is to minimize the phase deviation error. And the third objective is to implement the proposed method in ZigBee receiver. Contributions. We have made contributions in the following area. In simplicity, we are coming up with an optimal estimation algorithm that could replace or remove the phase synchronization circuit at the receiver. In terms of robustness, we have tested the robustness of the proposed method in the presence of Gaussian noise, non-Gaussian noise, and co-channel interference. Novelty, our proposed method shows that our receiver is working much better than the existing model, and we show the mean square error with different signal to noise ratio values. Cost, it's well known that the coherent detection is more expensive than the non-coherent detection. And our proposed method is based on non-coherent detection, which basically remove the phase synchronization circuit. Implementation, we have implemented or simulated the proposed method using MATLAB and Simulink. And we apply the concept in ZigBee receiver. Here are some previous related works which utilize Kalman filter as a tool for carrier signal detection. In 2017, there was a research recommends using Kalman filter as a digital carrier synchronization. And they apply the concept in global navigation satellite system. And they found out Kalman filter based detection is flexible and than the traditional technique with fewer samples. In 2018, there was research which uses and scented Kalman filter to improve the carrier tracking in GPS receiver with application in a vehicular communication channel. And they found out a significant improvement in the vehicular communication channel, especially in harsh dynamic environments. In 2014, there was a research conducted at Auckland University to use extended Kalman filter to non-coherently detect the Gaussian frequency shift key modulated signal, and they apply the concept in Bluetooth, and their findings were as follows. The extended Kalman filter outperforms the conventional receiver. Also, another research conducted at Auckland University, which uses interactive Kalman filtering for differential and Gaussian frequency shift key modulation, and they applied the concept in Bluetooth, and they found out Kalman filter is more accurate than the existing model, and it's robust, and it contributes to a phase error minimization. Introduction and background. In this section, I will lay the groundwork of this research by giving you a brief introduction on digital communication system and Kalman filtering technique and ZigBee technology. So what is communication system? Communication system is the exchange of information between two devices. One is called transmitter and the other is called receiver. And there is a channel which acts as intermediary device between these two devices. And the information that is sent could be plain text, image, or audio. The basic elements of digital communication: the source encoder, which converted the analog signal into digital, then gets passed into channel encoder. Channel encoder actually adds some additional bits into the coded bits in order to help the receiver find the error and correct it, and then gets multiplied with a carrier signal in digital modulator. Digital modulator is a device which actually contains on a sinusoidal signal waveform that could carry the coded bits into the channel. So the channel could be a wireless channel, which is subject to Gaussian noise, non-Gaussian noise, and then gets passed to the digital demodulator, which is the process of reconstructing the modulated signal from the modulated signal after it gets corrupted. Channel decoder do the opposite of channel encoder, removing the additional bits and correct any error that may occur in the communication. Source decoder contributes to convert the signal from digital to the analog, and the output will be the same information source that was sent. Here is a comparison of digital and analog communication system. We made a comparison in terms of the following factors. In terms of cost, digital is inexpensive. In terms of privacy, digital communication is its data is more encrypted than the analog communication. In terms of error correction, digital communication is capable of error correction, while in analog communication, it's impossible to correct the error. Bandwidth in digital communication is larger. However, synchronization in digital communication is difficult, and that's why we need to use a new technique that could actually comply with the most modern digital receivers. Phase shift key modulation. Phase shift key modulation is a digital modulation scheme where the phase of the carrier signal is changed in accordance with binary symbols. There are three classifications of the PSK. One is the binary phase shift key, and the second one, which is the quadrature phase shift key, and the third one, which is the offset quadrature phase shift key. So the phase shift key modulated signal is represented by this equation, where this portion represents the carrier phase, and the M is the number of possible carrier phases depending on the classification of the modulation, and G of T, which represents the signal pulse shape, and F sub C is the carrier frequency. So in BPSK, the number of carrier phases is equal to 2. And the representations are given by these two equations. And their implementation is as follows. Binary data is passed through non-return to 0 coding, which maps 1 to +1 and 0 to -1, and then gets multiplied with a carrier signal, and the output is the binary phase shift key modulated signals. So in QPSK, the number of carrier phases is equal to 4. So if you plug in the 4 in this equations, you will come up with 4 different carrier phases. So the final mathematical representation of the QPSK is given by this equation. And you can notice that we have 2 phase components. One is called in-phase component, and the other one is called the quadrature phase component. So offset quadrature phase modulation, actually it works as same as the QPSK, except the quadrature phase signal is delayed by half symbol period and is represented by this equation. This is the implementation of the OQPSK. Binary data is passed through digital coding, which maps 1 to +1 and 0 to -1, and then gets passed to a circuit, which is called serial to parallel conversion, which splits the bits into 2 things. One is called even bits, and the other one is called odd bits. And the even bits gets multiplied with a cosine carrier signal, and the odd bits is delayed by half symbol period to represent the offset, and then gets multiplied with a sine signal, and then they get merged here, and the final result is the OQPSK modulated signal. ZigBee technology. I think every one of you guys know ZigBee technology, which is a low data rate wireless personal area network, which is used for a short range distance communication system. It's promising technology due to its low cost, low power consumption, and its support of wireless mesh networking standard. ZigBee application areas. ZigBee actually is created specifically for control and sensor networks. ZigBee main applications exist in smart thermostat, remote patient monitoring, and tracking package in industrial environments. Its application areas in IoT is getting attention. Therefore, ZigBee sales are growing up and expected to dominate the market by 2023 and become the primary wireless protocol for the IoT. The ZigBee OSI reference model. So the physical layer and MAC layer are defined by IEEE 802.15.4 standard, whereas the above layers, network layer and application layer, are defined by the ZigBee alias. There are three classifications of the ZigBee frequency bands depending on the country. 868 megahertz band used in Europe, 915 megahertz band used in United States, 2.49 gigahertz band used anywhere around the world. Kalman filter. Kalman filter is named after Rudolf Kalman in 1960. It's actually a linear quadrature estimation. Kalman filter is used to predict and update the states of the filter. Therefore, with a prior knowledge of the state dynamics behavior, Kalman can estimate the next state of the filter and correct the estimate. There is a variety of applications that Kalman filter is applied to. In control, it's applied in self-tuning PID controller. In business, it could be used in to predict the stock price, and to actually it could be used in any business model that needs a projection. In communication system, it has been used for noise removal and navigation. In image processing, it has been used for remove the noise and actually to detect any feature in the image. In this slide, I will show you the recursive process of the Kalman filter algorithm. So we project ahead the state and its error covariance, where F is the transition matrix. And then we compute the Kalman gain with the assistance of a priori estimate and its error covariance error. And then we update the estimate with the incoming measurement, and then we update the error covariance. And this is calculated recursively. Extended Kalman filter works as same as the linear Kalman filter, except that the transition matrix F and the observation matrix H needs to be linearized. And there are two techniques of linearization that could be used. One is the Jacobian technique by using Jacobian matrix, or we could use Taylor series. Methodology. The methodology in this research is based on interactive Kalman filtering. In this section, I will illustrate the architecture of IKF and discusses its implementation. And then I will walk you through the OQPSK signal representation in ZigBee receiver. And then we will model the phase shift of OQPSK signal together. And then we will derive the general dynamic OQPSK state space model and also the OQPSK measurement equation description. And then I will show you the implementation of IKF in OQPSK modulated signal. the OQPSK signal representation in ZigBee receiver. ZigBee actually utilizes the OQPSK modulation scheme for pulse shaping. It uses direct sequence spread spectrum as its spreading technique, and then it's shaped by sine pulse, and the output of the OQPSK modulated signal in ZigBee is represented by this equation. Again, we have two phase components. One is the in-phase component, and the other one, which is the quadrature phase component, which is delayed by half symbol period. And the in-phase component is given by this equation, and the quadrature phase component is given by this equation. So the current phase is represented as follows: the previous phase plus the current mapping transformation from binary symbol to phase representation. If we plug in the equation 21 in equation 20, the previous equation, and equation 19, we can define the transmitted information of the kth symbol as follows. So we have the definition of the in-phase component, and we have the definition of the quadrature phase component. And you can notice that the IK and the QK are a function of the current phase. And also the current phase is a function of the previous phase and the current input. And the in-phase component and the quadrature phase component should be multiplied with the pulse shaping technique, which is a sine pulse shaping to reduce the effect of inter-symbol interference and smooth the signal to be suited to the wireless channel. The current phase transformation should be linearized, and we have to model a technique to linearize the current transformation of the input into a signal phase representation. So, as I mentioned earlier, the current phase is equal to the previous phase plus the current input, and we model the current input based on Euler method, which is nothing but it's a linearization technique, which is the slope of the previous, phase that shows the transition from the previous phase to the current phase, depending on the step size. So when the step size gets smaller, the accuracy of approximation will be higher. From now on, we will rename this portion of this equation as omega sub k, which is defined as the current phase minus the previous phase plus the W sub k, which represents the process noise having this distribution, zero mean and some standard deviation. So now we are ready to rewrite the dynamic behavior of the phase shift of the OQPSK modulated signals. And we need actually to derive the state space model of the OQPSK modulated signal in order to apply Kalman filter. So we have two states. One is the current phase, and the other one, which is the current input. And the current input, what I mean by the current input is the phase transformation from digital bits into a signal. So you can notice a priori knowledge of the current phase is required in order to find the omega sub k minus 1. And that will lead us to rewrite the equation as follows. the omega sub k is equal to the priori phase, which is the prediction, minus the previous phase plus the process noise. Also, we need to derive the observation matrix, and the inputs to the observation matrix is the received signal of the OQPSK modulated signal at time step t equal to k. And you can see here it contains on the in phase component and the quadrature phase components plus the noise, which is a white Gaussian noise, which represents the measurement noise of the in phase component, having zero mean and it's uncorrelated. So in this slide, I will illustrate the proposed phase tracking with the IKF. Since we already derived the state space, now we are ready to go with the derivation of our model. So the input to our model is the received OQPSK modulated signal, and then it gets split into two portions. Sorry. One is the in phase channel and the other one is the quadrature phase channel. And then we detect the phase. We use a circuit called phase detector circuit to detect the phase. And then we feed the phase into our model. So our model actually consists of two linear Kalman filters coupled together to be used as a priori phase estimate to the extended Kalman filter. And also we use the output of this estimate to be used as an observer to the second Kalman filter. So we can generate a phase coefficient plus a priori phase. And the output is the optimal OQPSK detection. So we need to apply a dual estimation to predict a priori phase depending on the previous measured phase signals. And as we learned from equation 28, the current phase is predicted based on the previous phase and the phase transformation as triggered by the current input. So in order to calculate the omega sub k, we need to have a knowledge of the current phase. In the meantime, we need to know the omega sub k to calculate the current phase. So to handle this case, a joint estimation is proposed to estimate the phase change. This is the final derivation of our proposed method. So we could actually propose we could calculate the priori phase recursively by this equation, where C sub I is the coefficient of the phase prediction, and the W sub K is the process noise having this distribution, which is a zero mean and some standard deviation. So in summary, we have two linear Kalman filters joined to be used as a priori phase to an extended Kalman filter, and as an observer to the second Kalman filter to generate the phase coefficient in order to help the first linear Kalman filter to predict the phase to the extended Kalman filter. And the output is the optimal OQPSK detection. Results and simulation. So we have binary data passed through the bit to symbol mapping. In bit to symbol mapping, we map each 4 bits into a symbol. So each 4 bits shape a group. Each 4 bits shape a symbol, and then gets spreaded into 32 bits and then passed through OQPSK modulation, and then passed through Gaussian channel, which is additive white Gaussian noise channel. And we add a scenario where another ZigBee device is interfering with the modulated signal in order to test the robustness and the quality of our proposed method. And we integrate the Kalman filter at the receiver to detect the phase changes, and the output is the optimal OQPSK detection. So Gaussian noise is nothing but it's a white Gaussian noise, which actually represents the modulated signal and plus some noise with some statistical distribution, zero mean and some spectral density of n sub 0 divided by 2. Results. So we actually compare our proposed method, which is the interactive Kalman filter estimated phase, versus the unfiltered phase, which is the existing model. So the Kalman filter, which represents the red color represents the IKF phase, and the blue color represents the unfiltered phase, and the black color represents the true phase. So you can notice that IKF tracks the phase changes more accurately than the unfiltered phase, and it handles the phase ambiguity here of the existing model, which shows the novelty of our work. So we tested the performance of our proposed method using mean square error with different signal to noise ratio, and we found out that IKF estimated phase has less error than the unfiltered phase. And this just in the presence of Gaussian channel. So we need actually to test the robustness of our proposed method with different scenarios, because ZigBee is operating at many nominal propagation environments. So we used a non-Gaussian noise, which is a harsh noise into the system, which is nothing but it's a mixture of Gaussian channels, 3 Gaussian channels with different means. So when we apply the non-Gaussian noise, still our proposed method give a good result, more than the unfiltered phase. Also, we tested the robustness of the proposed method in the presence of co-channel interference, and this is one of the scenario which is called crosstalk, and it occurs when 2 transmitting devices on the same channel compete for time to talk or send, which leads to crosstalk. We have tested the performance of our system in the presence of co-channel interference, and our proposed method still shows a good result with less error with, in the presence of different signal to noise ratio values. Contribution. So in this thesis, we use a Kalman filter technique to non-coherently estimate the phase changes without a phase recovery circuit. Robustness, we have tested the robustness of the proposed method in terms in the presence of Gaussian noise and non-Gaussian noise and nonlinear interference in order to ensure a high detection rate. Novelty. This research reduces the phase deviation error under different propagation environments. Cost. It's well known in the communication community. The non-coherent detection is less expensive than the coherent detection. Implementation and simulation, we implemented the integrated IKF at ZigBee receiver, and we tested the novelty and robustness of the new approach under different scenarios using MATLAB. Conclusion, this research introduced a new detection technique for OQPSK and lightweight solution for detecting the corrupted received signal and reducing the phase deviation error. So we proposed a cost-effective and simple solution based on non-coherent detection. The way that IKF is designed and implemented ensures a high detection rate against Gaussian noise, non-Gaussian noise, and co-channel interference. Here is some potential future work. This proposed phase detection can be implemented into hardware description language and can be embedded on the FPGA to generate the integrated chips. We can apply the same concept to some of the digital cellular standards, such as different MRI PSK. Instead of using extended Kalman filter in the IKF architecture, we could use sequential Monte Carlo with sequential importance resampling, and we could apply artificial neural network to track the phase changes. That's my publication, and feel free to ask any question.
Thank you so much, Dr. Ali, for this beautiful and informative presentation. It's a really great achievement, mashallah, tabarakallah, and you, mashallah, and you just present mashallah, a good work. Let's hear from everyone. If anyone have a question or anyone would like to ask a question for Dr. Ali, you can just open the mic and talk.
Thank you so much, Dr.
Salam.
Alaikum salam.
Yeah, you can start, Dr. Yusuf or Dr.
Because I am the host. That's why I just jumped in. So thank you so much, Dr. Ali, for the nice presentation. I really enjoyed it. Of course, there are some bits I could understand, but I was just wondering, of course, you have some potential future work. You said that clearly. Mm-hmm. But I'm wondering if there is any limitations for this work.
Yes, actually, there are some limitations when it comes to the hardware implementation. So it's not easy actually to fabricate the algorithm into a circuit in the labs. So we need to consult a company to do that for us.
Okay, thank you so much, Dr. Ali. Thank you. That was really a nice presentation. Thank you.
You're welcome.
Assalamu alaikum.
Wa alaikum assalam wa rahmatullahi wa barakatuh.
Can you hear me?
Yes.
Thank you very much for your informative presentation.
You're welcome.
Well explained.
Thanks.
I just have a few questions.
Mm-hmm. Go ahead.
The first one is, why didn't you consider a higher order modulation? For example, if we consider PSK, there is 8 PSK, 8 phase shift gain, or QAM, quadrature amplitude modulation. Now in the QAM we have 16, 64.
Okay.
This first question.
Yeah, this actually could be implemented in high order modulation scheme. It's very easy. You just derive the equation for the 8 PSK or 16 PSK or 64 quadrature QAM. So you can actually apply it in every high order. So actually why we are using the OQPSK, because OQPSK actually is modern techniques, and it's very simple to implement in the circuit, and it's widely used in most wireless protocol such as GPS. And so in GPS they use BPSK and the quadrature phase shift key, and OQPSK is actually an extension of the QPSK, except the quadrature phase channel is delayed by half symbol period. So this work could be extended to apply to a different modulation scheme, as I mentioned in the future work. Did I answer your question?
Yes, yes, very clear answer. Thank you very much. The other question is, in the slide 37, you said we need prior knowledge. When you say we need prior knowledge, that leads us to the coherent detection, whereas the carrier is generated at the receiver side. So I didn't get you there.
Yes, actually, if you remember, if you are familiar with Kalman filter, you need an initial estimate. So you just put any value. But here, we are not actually given an initial estimate. We let the system actually do that for us. There is an intelligence in our system that could do that for us to predict the phase based on this equation. Did you get it?
Yes, now it is crystal clear.
You're welcome. What's your name?
Actually, my name is Dr. Muhammad Al-Majdoub. I am familiar with the area. I am also networking and communication.
Yeah, it's my pleasure, actually. Yeah, please ask any question that...
So my last question is, what about the exact bit error rate? Does your system need any forward error correction?
Actually, this has nothing to do with the proposed method, because actually what we are doing is to detect the phase and try to make optimization on the phase detected. And after that, it will go to the digital decoding to figure out the signal. So digital decoding actually works with any phase detection. So has nothing to do with the IKF.
Okay, Jazakallah khair. Actually, you cleared all my questions. Very good presentation. Thank you very much.
You're welcome.
Thank you, Dr. Muhammad. Dr. Yusuf, please, if you have any question, you can over the mic and just ask Dr. Ali.
Assalamu alaikum.
Wa alaikum assalam wa rahmatullahi wa barakatuh.
This is Ahmed Al-Hifdhi. I'd like to thank you for this presentation. I'd like to thank everyone who is trying to provide us with this good information. Actually, in this presentation, what caught my eyes is that using the ZigBee technology. It's not actually a question about the presentation. It's only a suggestion that if we can do something like a cyber physical system using the ZigBee, I think it's going to be nice for our college and for our students too, because there are so many projects that we can provide using ZigBee.
Yeah, you are right. So we could actually detect any jamming attack to the ZigBee network. So using this technique, this will improve the accuracy of detecting the jamming attack into the network. And it's
Exactly.
and right now, one of our colleagues, his name is Dr. Walid Dosari. He's working with the Ministry of Defense in Saudi Arabia to detect the jamming using the Kalman filter for the drone. So this has also potential work in this area.
Exactly. Thank you.
You're welcome.
Thank you so much, Mr. Ahmed. And if we still have any question, please just jump in and you can ask. Okay, great. So I think we don't have any more questions. Thank you so much again, Dr. Ali, and inshallah we'll see you soon, inshallah, here in the college, and collaborate all together to work in research and in different areas, inshallah. Thank you so much. Thank you everyone for attending this presentation and this seminar by Dr. Ali Alqahtani. Thank you for everyone who made this happen, especially thanks to Dr. Yusuf, who organized the event and organized everything. Thank you so much, and have a good night.
You're welcome, Dr. Hani, and thank you so much for organizing. And also, I would like to extend my thanks to Dr. Yusuf for organizing, who organized the event. And thank you all for attending.